Hi, everyone. I'm Kilian Weinberger. Quick thing, if there's any questions, please don't hesitate to raise your hand and ask questions during the talk. I prefer that actually, because it's probably if something is unclear to you, it's probably unclear to multiple other people, and it just helps to clear things up while you go. All right, so let me start with a hopefully non-controversial statement that LLMs are amazing. And I'm not going to go into how they're amazing because you all know, they're incredible. Like even my mom actually is using LLMs every day now, but they're also not perfect. And once again, I'm, not going into the details. There's many concerns about LLMs because the media is full of both of these two topics. And, they use a lot of energy. There's a token shortage, and they're obviously always too slow and they hallucinate. And, there's all those complaints we have with LLMs. What I want to talk about today is essentially two architectural limitations that my group and I identified and we would like to address. That basically kind of inherently are kind of the way LLMs are constructed right now. These are kind of problems that we need to overcome. Like the current architecture of LLMs is essentially too limited. And here are two fixes to these two problems. And the first thing we're going to talk about is what we call limited memory language models. This is a small tweak in how language models are designed. They're called LM. We actually pronounce them lam. And this is collaboration with the main student who's leading this is Lingxi and several other my students, and of course you have Artsy who just introduced me, and then Jennifer Sun. And the main architectural limitation that we're addressing here is that we claim that neurons are actually a terrible way to store data and in fact to store facts. And let me illustrate this with a little example. So imagine I give you two sentences and you can read them now. By the end of the talk, I'm going to quiz you, right? And you're going to get a grade on how well you remember all the facts. Right? And the first sentence, in this case, is, hopefully pretty easy to remember. It says Napoleon had a mother who gave birth to him somewhere. So, you may not know anything about Napoleon, but if you know he's a human, well, he had a mother, and mothers give birth to their children, and they do that somewhere, right? So these are all facts that are true, but also every single one of these facts can be inferred from something else. These are facts that generalize. If you know this, if you've understood this about humans, then you know this about everyone, right? I may not know you very well, but I know that your mother gave birth to you. The second sentence is very different, right? Napoleon was born on August 15th, 1769 in Ajaccio, Corsica, to his mother, Letizia Bonaparte, right? So here, there's a lot of facts in there that are very, very specific, right? If you know something about humans in general, you still don't know that Napoleon was born on August 15th. That is a very, very specific fact. And if you want to remember this, probably what you do is just write it down, right? Because actually, it's really, really hard to remember all these little facts, right? Because neurons are actually not a great way to store these kind of facts. So the first one, we call this, is basically general knowledge. It's low information content. Whereas the second one actually has very high information content. You need many, many bits to store that information. Right? And it doesn't generalize. So right now in LLMs, I claim we actually have three categories of knowledge that we try to squeeze into these LLMs. The first one is language competency. Like language competency is essentially being eloquent, talking naturally, understanding grammar, understanding how language works. We know LLMs are really good at this. Right? LLMs are really eloquent. The second thing is common knowledge. That is, Napoleon had a mother. Like this is stuff that generalizes. This is stuff that everybody knows. This is stuff that you can infer about someone even if you haven't read their Wikipedia page because it's actually all over the place, right? All humans have mothers, right? The last category is factual knowledge. Like this green stuff here. These are very, very specific, facts that you would only find on for example the Wikipedia page of Napoleon. If I read some other Wikipedia pages, you won't find out the birthplace or the birth date of Napoleon, right? This is the stuff that's very, very specific to one particular entity, and I claim this actually takes a disproportionate amount of of the energy and of the neurons that we in these large language models, right? This is something that you cannot compress. And if you know my birthday, it doesn't tell you anything about Yoav's birthday, right? So you have to memorize each one of them. There's no way around it. So I claim neurons are actually really, really good for the first two categories, right? They're great for language competency. They're great for this common knowledge, but they're terrible for the specific knowledge, right? We are wasting all these neurons. You actually, storing them is really, really painful. You have to go over the data many, many times, and you may still get it wrong, right? Where does hallucination come from when neural networks actually get these kind of facts wrong? Well, neurons are a really bad way to store this kind of information, but it turns out there's a really, really good way to store this kind of information, and we've worked on it for decades, and it's called databases, right? These kind of facts should be in databases. They are great data structures. They're well understood. We know exactly how they work, they scale, and so on. So this work is about separating the knowledge, this kind of knowledge, out of neural networks and putting them in database. And we want to do this right from the start, during pre-training. So when you, very, very beginning, the neural network is designed that it actually doesn't have these specific facts inside its neurons. The advantage is that actually, there's multiple advantages that fall out of this right away. One is that the models can now be much, much smaller because you don't actually have to store all the stuff, inside the neurons. You don't actually also have to retrain them all the time, and some facts get out of date, you just update it. It's much faster to train and actually much cheaper to operate because they're much smaller. You need less electricity, right? They're smaller and so on. The advantage of having things in the database is also that databases can be huge, right? We know how to extend databases, right? We know how they work. They're really, really powerful, and it's interpretable, right? You can actually look at the database and you know exactly what's going on inside of it, right? Whereas the neurons, you don't know what's stored in there, right? Further, if some facts change, for example, a new president gets elected, well, you don't have to retrain your model. You just change the entry in the database, right? And finally, and this is very, very important, when you populate the database, you can put in grounding. You can put in links to where you got the information from. So when the neural network says something and it queries the database, you can actually have a certificate that tells you where that knowledge came from, right? All right. So here comes the point where usually people go like, wait a second, isn't that RAG, right? So RAG is retrieval augmented generation. And so when you, for example, enter something into ChatGPT or Claude or whatever, like there's this little thing of searching the web, right? And so basically what happens is the LLM searches the web, finds some pages that are relevant and pastes them into the context. So now actually the model is more informed. RAG is very, very popular, but RAG is actually kind of the opposite of what we want to do. RAG takes a model that's trained and then actually puts in external knowledge, right? What we want to do is take the model and make sure there's no knowledge inside that model, right? We don't want the model to know anything, and we want the model to know that it doesn't know anything. And then all the knowledge should be outside in some database. When I talk to top people in industry, they usually immediately get it because those are exactly the problems that they suffer from all the time. Right? So for example, I'm working with a company that builds chatbots for customer service for airlines and so on. And one problem they have is that, for example, a customer talks to the bot and says, my flight is delayed and from JFK to LAX or something. And the bot suddenly says, well, actually, this competitor airline has a much better flight, actually. You should just use that one, right? Another issue is actually game designers, right? They now use NPCs, non-playable characters, so, computer characters, and they now are LLM powered. So let's say you're in medieval game and, you talk about whatever, like, they're saying the 1600s or something, and you talk with a person in this game, and suddenly it can tell you all about PyTorch libraries and so on, right? Because it's an LLM and it knows way too much that it's not supposed to know, right? Finally, actually, Google and Apple, they're really, really interested in putting LLMs on devices, right? They have to be really tiny. They don't want them to know a lot of stuff. They want them to operate with the knowledge that's on your phone. They want them to operate with your email, with your text message, etc. So bottom line is, what people really want is to control the knowledge of a language model. So how do we do this, right? And essentially, it comes down to a modification of the training data. So what we do is we actually did this on Wikipedia. So we did a prototype where we pre-processed all of Wikipedia. And so here's an example sentence from Wikipedia. Napoleon was born on blah, blah, blah. And I highlighted in green all the specific knowledge that basically I don't want the model to know, right? And in blue is the common knowledge that, it's fine to know. Like Napoleon was born, well, that's no brainer, but exact date, right? We don't actually want the model to remember this. So what we do is we actually take the sentence and we rephrase it into Napoleon was born on, and then we insert a lookup table, a lookup token, a very specific token that just says, look something up in the database. And then we look up Napoleon's birthday. And then we pretend there is this magical database that actually has all the answers. And we pretend that this database actually returns August 15, 1769. And then the text continues. So this is basically something we are inserting into the text, right? As if this was, you just modify the text, just editing, text editing, right? We just insert this token lookup, and then here's basically the entity, and here's the property, and then, here's what we imagine the output would be from this database if it existed, right? Yeah, question.
So it looks like a copy.
Yeah. So very good. So the question is looks like a copy. So this is exactly what we want. So this here actually comes from the database, and then the language model should take that information and produce this string here, right? And so the nice thing is it doesn't actually have to know that knowledge anymore because it just saw it, right? It just came from the database. It just saw the string here, so it just has to copy it, right? Does that make sense? So a little like if you have a student who takes an exam and you just always give them the answers in a little cheat sheet, right? What is the student going to learn? They can just copy from the cheat sheet, right? That's essentially what it is. Here we go. So we have these three, we categorize these three different entities, and we just do this change. The nice thing is what you can already see is now, the problem with specific knowledge is that it doesn't generalize. You have to memorize it, right? Now, we basically turn into something that generalizes, right? When was Napoleon born? Napoleon was born on, look up Napoleon's birthday, right? When was Greg Morissette born? Look up Greg Morissette's birthday, right? So even if I don't know you, suddenly I can actually argue about your birthday, right? Even if I haven't memorized it. So we basically achieve this generalization. Okay, so how do we do all this transformation of the data? And well, the answer usually, when you work with AI and you have a problem that you don't know how to do, the answer is usually more AI, right? So here's what we do. We actually take, GPT model, and we basically ask it, right? Like, what is the common knowledge? What is the specific knowledge? And you just ask it to make these modifications. That's very expensive, and you want to do this on the whole training corpus. So what we do is we just do it for a couple, 100 pages, and then we basically train our own model to actually do, basically, distill that into a small model just by learning what the output should be. And actually turns out that's very easy to learn. And then once we have our own model, we could actually run it over all of Wikipedia in a couple of days and modify as much as we want. We have a little step in the middle, but actually once we make these annotations, we actually then have a second pass through it to make sure everything is still fluent. It's just a cleanup process. Okay. So one thing I hadn't answered is, where does the database come from, right? When we change this text, we assume there's this magical database, right, where all the facts lie in. Well, once we've changed once we've actually created, these entries that come from the magical database, then we can actually just create that database ourselves, because we have this, for this key and this property, actually we should have this value here in the database, right? So we just go through the corpus and we just populate the database after it's created. So that's a very easy step. How do we train the model? And it turns out that's, again, relatively straightforward. We basically just do next word predictions. So large language models, as I'm sure many of you know, are basically just trained by give it a sentence, predict the next word, and so on. So we just give it this modified text and we say, always predict the next token. So after Napoleon, you want to predict was just like normal, but after here, you actually want to predict the lookup token, right? So you're basically teaching the model, right? When you want to know something, you just got to look it up, right? And it basically learns that syntax. And I think that was your question earlier, right? How does it know to look things up? Well, basically, you just, doing training, it basically learns if it wants to know something, here, put in the lookup token, and then actually just here's the attribute of, the entity they want to look something up about, and there's the specific property here. But here comes the trick. When you actually get this response from the database, here we mask out the gradient. So we are not learning this. This is really, really important, right? Because we don't want the model to learn the stuff that's in the database, right? So this here comes, this text here, we just don't do any gradient updates, but here we do gradient updates again. And that goes exactly to what you pointed out earlier. What the model now learns is that the moment it generates these tokens, it learns, oh, I just have to copy what I saw previously. All right, does that make sense? Any questions?
Is there some
It's just like most tool many entries like keyword base, as opposed to say like you're talk about elements in a periodic table.
Oh, the question is like, is this only useful for, you know, human beings or something, but not like, if you have elements like in the periodic table? And the answer is no, it can be any knowledge, right? Like it can be any specific facts. Like, and you can think of this actually as a knowledge graph, right? Where you have entities and then you have relations. This could be a pretty vast knowledge graph.
So, but understanding what's the value, does the value come from scale that you're compressing the scale and take it to the.
Yeah, you can actually have a massive database, but you have a tiny model, right? Because the model, all it knows is to look things up, right? It can be really, really small, right? And really fast. Yeah.
Well, the night was just good.
Right. And so, this is a reference, like people have done, use Prolog or something to look to, the old AI research basically offload a lot of stuff into databases and build knowledge graphs. And what do you do with contradictions? It's okay. We are still working on this. There's some follow-up work on how to actually make this even simpler. You have to clean up the database, but it's the same actually. If you were to train a language model just on the raw data, you would also have these contradictions, right? It's actually, by the way, there's a very nice follow-up paper by Yair Weiss and Yoav actually. It's right now in the submission where they actually, just make the lookup token without actually these two entities. Basically, just saying Napoleon was born on look it up, and it just uses the previous context to basically to figure out what you actually want to look up. So that's very, very even more efficient. Faye.
So this sounds like you essentially put two use in pre-training stage, right?
So I put what?
Two use. Like a
True use. Yes, exactly.
Now, my question is, for mistake for gradient propagating, not only you actually have to look at the return time knowledge, but also the proper invocation of the right API. Because suppose your database supports multiple way of extracting knowledge, then you have to know which API is correct. Right?
So basically, Faye just made the connection to tool calling. This is basically a tool call. You can view this as, this is just an API. But in this case, we only have one. Like, there's no choice about what API you want, right? In our case, and the LLM was a really teeny little baby, and we just did pre-training, right? It already kind of had access to this particular tool call, right, from the beginning. So it knows how to do this very, very well.
Okay, thank you.
Yeah. Okay, let me maybe continue, and then all right, so what do we do during inference? So when you actually then generate text with this model, you just, the language model just starts talking, and basically at some point it just generates this token, looks something up, it gives it the attributes, and the moment this happens, we actually initiate a database lookup, we populate this orange stuff, right? We teach it for us this too, right? And then given this, we let the language model continue, and basically has now learned to actually deal with this knowledge that comes from the database and can incorporate into the text. Okay, two questions that immediately come up. Like the first thing is, what if, the key actually doesn't exist in the database, right? And this is something of a design choice, right? One thing that's nice is when you look something up, for example, I look up Greg Morrisett's birthday and it's actually not in the database. Well, maybe that's good, right? Maybe actually I'm not hallucinating something. I actually get back, I don't know, right? And I can actually admit that I don't know something. What if I get the birthday a little bit wrong? For example, I say birthday instead of birth date or something like this. And so one simple solution for this is you have a fuzzy lookup. So you basically just embed these vectors, like these lookup keys as vectors. And you just do a nearest neighbor match. And that slows it down a little bit. That's a trade-off. But, it gives you more database hits. Another option actually is that during lookups, you can actually have a prefix tree where basically you only allow it to generate tokens that actually are valid keys in the database. So this way you actually never have a database miss. That's very, very fast to implement. You actually tried both of these and both work. Yeah, question.
How do you deal with context of the same information? In other words, if somebody wants to know what is our total sales for the year, a sales rep was looking probably for their sales. A sales manager might be looking for, or CEO. So it's the same question. So
but what if context matters, right? So, and this is actually essentially the paper that's really on a submission in Europe, where basically you just take the previous context and basically learn a latent vector. and use that as a lookup. So then it would be different. If you look up for sales numbers, I look up for sales numbers, like depending on what the text was beforehand, you would actually get different keys.
The going to be the lens of the user who's actually asked for the answer.
That would be part of the context, right? We evaluated this. One thing is language models are typically evaluated in perplexity. Perplexity is just a metric of how surprised you are when you go through a certain word. So if I say, for example, I love eating tables, right? Tables has a word of high perplexity. You probably didn't see it coming, right? And so this is essentially, the lower the perplexity, the better the language model. You can, here test the perplexity value as we are training it. And so, here we lam-lam-5, this is exactly the same model, but we train it without lam-lam and with lam-lam. And you can see there's a massive drop in perplexity, right? And this is actually not surprising. This is exactly what we expected would happen, because it's much, much easier to say Napoleon was born on, look up Napoleon's birthday, than actually the exact date, right? So it just makes the task much, much easier. But that's the point, right? So this is kind of a sanity check. We tested it here on some, fact score is actually is a very specific data set where you generate packed load and biographies of entities. I'm not going to bore you with the details, but essentially what you're doing is you're testing language models. This here is how good they do at natural language understanding, this is their utility, and this is how factual they are. And what you really want is you want to be high. These are small models, these two, and we lam-lam find them both, and you can see that they basically, the utility stays the same, but they become much, much more factual, right? So they get just through the roof. And if you look at this carefully, actually, one thing that's really exciting is this is a model with 176 million parameters, and it totally outperforms models that actually use over 1 billion parameters, right? So these models now punch way over their weight class. This is, what is exactly what we're hoping. One thing, we did some tests of this actually maybe still remember some facts, right? So we actually look at the perplexity of these factual information, and you can see that actually, like normally when you train the, basically starts memorizing these factual information. In our case, actually, it really doesn't, right? So, it's just as good as random initialization. It really doesn't know any facts. You can also test this here, and doing testing, we suddenly remove the database, which is of course really unfair, right? The poor model, relies on the database, and we just suddenly remove it, right? And then actually the performance completely tanks. Last but not least is like a really cool application for this is forgetting, right? That's a really big deal nowadays, right? All these companies spend millions on training these language models, but actually, for example, in the European Union, users have the right to be forgotten. So if you are a user, they used your data, you actually have a right that, for them to remove all your data, within a certain amount of time. Right now, there isn't really a good way of doing this, right? You have to retrain the model. There's some weird gradient descent methods that they don't work very well. Here's actually, a very simple test we did here. So we took a data set that's a union of two different data sets, the green and the blue one. We trained basically two models. One is on the union and one is just on the blue data set. And if we take, essentially what you're doing is you look at these two models and you try to remove the green data from the first model and see how different it is from the model that was only trained on the blue data. And with lam-lam, this is really, really simple, right? Because you just annotate the database and say everything that comes from the green set, you just remove, right? And so it doesn't know it anymore. It works really, really well. And this is what you see in this graph. This is actually a statistical, you do a significance test. How different is a model where you remove data from a model where you never even saw the data? And you want this to be insignificant, so you want a large p-value. So here's our lam-lam model. If you remove data, actually, it's just the same utility, but actually, it becomes indistinguishable from a model that was trained without that data. So we have a really, really effective way of removing data from a model. All right, this is the first part of my talk. So this is essentially, just to summarize, the idea basically of lam-lam is that we externalize memory and get it out of the weights and move it into a database. And has many, many advantages. Any questions at this point before I switch to the next part? Yes.
I have actually two questions. Number one, the lookup token. Do you encode how to look up part? I mean, that's clear what to look up, but how to look up? Is it encoded during the
The lookup token is just one token, and that actually then triggers our code to look something up in the database.
So the how part is?
That's just hardwired. Yeah.
Okay, so is it then interoperable, for different kind of databases? Somebody may be using X and Y and Z.
Yeah, that's all behind the scene, but the language model doesn't have to know this. Right?
Okay. And the second question is, what about the distillation? Like right now, you're pre-training from scratch. How about leveraging what already is out there and then doing some
Right.
distillation and reach here?
Yeah, so right now we're pre-training from scratch because we actually want the model to be tiny. You can also take a model that already exists and fine-tune it and basically just teach it to do these database lookups. That works. And we actually, we did this. It's very, very effective. The problem is you still have all the knowledge that the model was trained with. So sometimes you may have a conflict. Let's say the president changes. Your database says it's now the new president, but your model weights say it's the old one. That's something you might have to deal with in that case. Yeah, Greg.
So, what if you went back from a database query to a RAG query? Like just did a Google search at that lookup. How does that compare to?
Yeah, we have some. I actually don't have the slides here. We did comparisons with RAG in the paper. Like, if the model is pre-trained with our setup, it's much, much more effective because basically it knows exactly what to look up. It's really, really good. And actually, we also have a paper currently on submission that actually does reasoning, where actually it basically does chain of thought reasoning and looks facts up right and left along the way, right? And then actually it can become very, very powerful. Okay, maybe I take 2 more questions. Yeah.
You've shown differences in perplexity with GPT-2, and I wonder, this is somewhat of a manual process to solve in the pre-training, right, to clean all the data based on facts. So I wonder that if you're looking into the out of the shelf foundational model and their progress, do you think that they would eventually just pass it with more efficient tool calling or capabilities at the end, and then like it will beat the manual process?
I mean, it's a question because the models are very, very small. Would that still work for large models? So in some sense, part of the point is that we want very, very small models. I do actually believe that this is also the right way to go for large models because right now, one reason they are so gigantic is because they know the entire internet, right? But in an extremely inefficient way, right? So I do think that that's essentially the future, that, basically you just train these smaller models and you can just update the databases as you go along. Yeah, last question.
Thank you. I was wondering if you could use this to solve the sort of permission problem where you might have sort of a model you build for an organization and different users have different.
Absolutely. Yeah. So basically, because in the same way that with the data, similar to the data removing part, right? You could basically say, well, some users have access to the green database and some, only have access to the blue database. Absolutely. Yeah. Okay, very last question, Israel.
This may be a trivial question, but I just wanted to ask, how would you expect the model to perform if you asked what other famous people were born on the same day as Napoleon?
Yeah, very good question. Very good question. So what if it's not such a trivial lookup, right? But it's, and that's actually where you need this reasoning that I didn't talk about today. It's basically you would need a chain of thought reasoning, right? And then but because the database is essentially a knowledge graph, you're essentially traversing the knowledge graph that way. Yeah. All right, good. Let me get to the second limitation that I want to address. And that's also a fundamental limitation, maybe even more fundamental, of language models. So the first one was that basically they store all this information inside the neurons, which is not a good idea. The second one is that they are trained on next token prediction, right? And, we're all amazed how well that works, right? But it's limiting, right? Why is it limiting? It's limiting because it's myopic. So the way these models are trained, they're very, very good at predicting the next token, but they don't actually think much ahead. It's a little like, imagine you're a stand-up comedian, you're standing in front of a crowd, right? And you start a joke, right? But you don't actually know how to make it funny at the end, right? You just hope that by the end, you're going to come up with some funny punchline, right? That is the life of an LLM every single day, right? So we start something and it basically just hopes that at the end, it kind of can steer it towards something that's actually meaningful, right? Luckily, English language, or, language in general, human language, is flexible enough that most of the time that works, right? But sometimes it corners itself and actually it can't really get out of it. And then that's typically when hallucinations happen, or, it says weird things. So how do we get out of this, right? And how do we make sure the language model doesn't corner itself? And I came to 2 different solutions. The first one is what I call the MacGyver solution. Does anyone remember MacGyver? Yes. So it was a show in the 90s. And basically, every episode was the same. MacGyver always got stuck in some, so you think there's no way out, but then he always is really clever and he has some idea how to get out, right? And so essentially what I mean here is, well, if your language model is just much, much bigger and has learned many, many more things, then actually you will be smart enough that actually you will get out at the end, right? So if you're a much smarter comedian, you will come up with some clever way of making the joke funny at the end, right? That's essentially what OpenAI and Anthropic are doing right now. That's the one approach to this. It works, but it's very, very expensive, right? Because you have to train these massive models and you need a lot of data. The second one is the Princess Bride approach. I don't know if people know the Princess Bride, where it's like the battle of the wits, where, the person argues himself, all of this. And essentially what you do here is, you basically just let the model talk, have an internal dialogue, right? So, and most of the time, these language models actually nowadays hide these tokens, but here actually, I showed them. And so here's a very simple prompt that I did, is like say hello, right? And the language model then responded by, these are kind of the internal thoughts that usually you don't see. Okay, the user wants me to say hello. Let me think about the best way to respond. I should keep it friendly and simple. Maybe add a smiley to make it warm. But wait, should I use an emoji or just text? The previous response used a smiley and so on, blah, 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 right? It's like a middle school kid like talking to their crush for the first time, right? Totally overthinking, right? Really, really nervous, right? And at the end it ends up saying, hello, smiley, how can I assist you today? Right? So you're wasting all these tokens, right? There's all these tokens that are going on internally, right? But, like now it just says thinking, right? But, the language model is going, spinning its wheels, right? It works, but it's also not maybe the most effective way of doing this. So there's an alternative. There's a very different architecture that's very popular, and that is diffusion models, right? So diffusion models, you've probably all used them if you want to generate images. And diffusion models have the property that they are not autoregressive. So that means in an autoregressive model, you just generate these tokens one by one. So an image that would be, you start with the top left pixel and you generate one pixel after another. You slowly generate all these pixels. And you can see how that is very, very limiting. If you do this, it's really, really hard to get a globally coherent image that way, right? Diffusion models are magic because they can actually generate the whole thing in one go, right? There's basically one global generation. How do diffusion models work? They're actually really, really simple, right? So essentially what you're doing is you just have some images, you download them from the web, and you add noise to them and then denoise them, right? So here you have this noisy image. You don't know, the model doesn't quite know what that is. Could be a pancake or something. But actually what you do is you give it some description. You give it some hint. There's an oil painting of a white man. Does anyone know who he is? It's Gauss. That's right. So I added Gaussian noise to Gauss. And so I'm trying to denoise this image, but I tell it's a white man. So then actually it learns to denoise these images, right? And then you can train this very, very easily because you can take infinite amount of data from the internet to just many, many, images with descriptions, and you just always add noise and then you try to denoise it. How do you then generate new images? And it's very, very simple. You basically trick it into doing this, right? You give it random noise, and this is random noise. There's nothing. There was no image visually. And I tell it, can you please denoise this? And by the way, it's an astronaut riding a horse, right? And so the model actually then tries to denoise this, and it removes the noise. And I say, well, keep denoising, right? There's an astronaut riding a horse, right? Trust me, right? And slowly, actually, this comes, this surfaces. Because then you're telling it what it's supposed to denoise, right? So it actually slowly comes out, right? That's the trick. And if I give it 3 different amounts of noises, it actually gives me 3 different astronauts riding a horse, right? And the reason, this was chosen, this bizarre sentence was chosen because at the time there was actually no image on the internet of an astronaut riding a horse, right? Just to show that this is unique, right? That it can actually do new stuff. So the question is, the nice thing is we want to use something like this because it's globally coherent, right? So we would love to kind of make more global decisions in our text generation. So how can we do this? So, one of the problems is that, well, text is not so easy to add Gaussian noise to text. It's kind of weird, right? How you do this. The other thing is, we want the global thinking property, the non-myopic property of these models. But I don't want to kind of reinvent language models completely. Like a lot of money has gone into training these language models. So a lot of effort. So, we don't want to throw out the baby with the bathwater. By the way, I just want to point out, I'm very proud of this image because it was very hard. Like GPT-5 refused to generate an image of a baby being thrown out of a window. And the trick is we do it in a latent space. So, there's something called latent diffusion. People also do this in computer vision. And essentially, if I have a text, some text, I can actually use an encoder to basically get a latent strings, a bunch of numbers that essentially encode this text. And then I can decode this again and get the text back. So this is just an autoencoder. But once I have this representation is identical to this, right? This I can use the decoder and always get the text back. But this here is now continuous numbers, and I can just add Gaussian noise. And now I can just train a model that I can generate text on the internet. I can just get this representation of it, and I can just add noise and say, learn to denoise it, right? That's what I need for a diffusion model. I need some entity where I add noise, and then I learn to remove it. So I can do this. I train this diffusion model, and it learns how to denoise. And then actually, what I can do the same thing as with images. I can just start with some noise, just pure noise, and say, denoise this for me. It generates some latent code that I then decode, and then actually this way I can create text out of thin air, right? By just giving it noise and saying, this is some latent code. You just gotta denoise it, and then it works. This is something we published a few years ago, and so now we want to use this to fix the limitation of language models. Right? Remember, the limitation of language models is that they only just predict the next word. They don't look ahead, right? And so basically they corner themselves into weird situations. So what do? We have a language model that basically, the way this works is, language models, they always predict a word. Like you still give it the first word, then it predicts the next word, given the next word predicts the third word, and so on, and they keep going around. And what we wanted to do is to sometimes, I call it stop and think, right? Like actually when I ask you something, think about what you're going to say next. Don't just start blabbering, right? And the issue is that right now, each token has exactly the same amount of thinking process. You have one pass to the network, and then the token is there, right? You can't say, oh, wait, that's tricky. Let me just think about this. Language model can't do that, right? They only have one pass to the network. That's it. So we want to change this. So what do? We just allow the language model to trigger a mechanism that's actually a diffusion model inside of it. So a language model inside of it has a latent code. That's a latent representation. That's basically the newer representation of what's going on right now. And we basically train a diffusion model to generate this newer representation. And the nice thing is, diffusion model, we basically take the same architecture to go from the noisy version to a noise-free version. So we can just take as many passes as we want to slowly go from the noisy version to a clean state. So it's essentially like thinking, right? You have some vague idea initially, and we just make many, many passes, as many as you want. You can say 10 or 100 or 1,000, depends what you want, right? Depends on how hard you want to think. And you basically get a latent code that essentially tells you, what your current thinking is, what your current thoughts are. And then you keep decoding. That's the idea. There's some architectural details. Maybe I skip those. The trick is, just for those who kind of really like the weeds, you actually have two different MLPs here, one for diffusion and one for language. So we just switch between them, and this makes it happen. Okay, so and how do we train this? Like during training, we need to tell it what is latent, what should it be, right? What are your thoughts right now? And what we say is you just actually take the average of the future tokens. So basically saying, when you think, right, what your thoughts should be is essentially average of the future, right? Like you kind of should have a vision of what the future is. That's the idea. Let me show you some examples. This comes from Bachman and Nagarajan. Is a nice example that actually shows this limitation of the myopic setup. So here we have a graph, right, the star graph, and we can feed all the edges into a language model, right? Then it understands the graph structure, and then we say go from the middle to a specific end. So go from 31 to 10. Okay? So it's what it's supposed to output is, okay, I'm at 31, I go to 2, I go to 4, I go to 9, I go to 10. I'm done. Right? Turns out language models can't do this at all. Right? They're terrible. Why are they terrible at it? Because at the very, very beginning, you have to make a choice which direction you're going, and you have to think ahead. Right? You have to know, if I want to go to 10, I can't go to 1 because I can't recover here anymore. Right? I have to go down this route. So you have to think like 5, 6 tokens ahead. Language models can't do this, right? They basically just take the first token and say, well, I'm going to figure out some way of getting there, right? So they go up 1, 20, down, can't recover from here anymore, right? So we can see here actually, the more complicated the graphs we're making actually, this here is how many paths we have. Like the models actually essentially get 0% chance. Like this is random, if you just take a random path, and this here is an autoregressive model, they actually completely tank, right? They can't do it because they're too myopic. If we switch on our thinking, they actually get it right every single time. right? There's just a little bit of thinking beforehand. If you just think about it a little bit, you can figure it out, right? It's not very hard, right? So that's, it's just a little proof of concept here. Let me skip this. And we also do this for story generations. Once again, we generate stories, and then afterwards evaluate them on coherence, plausibility, and so on. And the point here is that our model, that's very, very small, right? This is like, 0.96 billion parameters, is about as good as a model that's like an order of magnitude larger, right? Just because it does a little bit of thinking, right? So one reason these models have to be so big is because they're not thinking. Right? They have to kind of get out of it at the end. So if you just put a little bit of thinking in, you can actually make much, much smaller models. Let me just, I'm almost done, and then you can ask some questions at the end. You also do this for math. I'm running out of time, so, it helps particularly in mathematics. And actually, here's a really fun thing, because my student had this idea of just give it Sudoku puzzles, but you have to start from the top left and insert all the numbers, which is really nasty, right? At some point, you basically, here you couldn't put in a 2, I think, or a 5, but if you put in a 2, you actually can't solve this guy anymore, because there's already a 5. So that's very, very hard if you don't look ahead, right? But if we do our little bit of thinking, actually we get significantly better numbers out of the box, right? All right. So in summary, the point is that, one limitation is that they are very, very myopic. The language models just think about the next token, but we can make them such that actually they think ahead, right? And we should, we humans do the same thing. When you ask me a difficult question, right? I think, some people, they just keep blabbering. We all know the type. But we hope that some people actually think a little bit before they answer. So in summary, the first one was, neurons should not be a database. A database should be a database. And instead of next token prediction, we actually should have a little bit of global planning, and then we do a lot better. That concludes my talk. I want to thank all my students and collaborators who did most of the work. And if there's any time, we can do maybe 1 or 2 more questions. Thank you. Yes.
Thank you. This is really cool. Maybe like a year ago, we've seen Inception, a company that did this type of diffusion text synthesis. And, we thought it was really fast and really cool, but like it wasn't very smart. So I'm kind of curious what has been the advance, say, over the past year or two?
It's a little different. So Inception Labs, actually, one of the co-founders actually faculty here at Cornell. They got a lot better. So the reason they weren't as smart is because they just started. So, OpenAI had like a 6-year head start. The new models are actually very good, but it's actually a bit different technology. It's discrete diffusion. So they do diffusion in the text, whereas we do diffusion here in the latent space. So they actually, I don't mean this in a negative way, but they throw the baby out with the bathwater and then actually get a new baby, right? So they actually retrain the whole model from scratch, which is something we didn't want to do. We want to leverage the original model.
Thank you so much.
Hi, thanks so much.
Wait, I don't know who's talking. Where is it? Oh, yeah, okay, good.
How far can you think ahead? Because I assume you need to parameterize a bunch.
Good question. It's basically something during training, it's a parameter. And we actually changed it a little bit. For Sudoku, actually, you want to think ahead for the whole puzzle. Right? For other things, maybe, just 50 tokens or something. It depends.
Is this during training or?
So you choose actually during training, because the way we trained it is that you basically average the tokens of the future, right? In Sudoku, actually, we had to do a little bit of clever trick again to make sure you don't just, because then it can't be totally order invariant. You could probably also train it actually where you vary how much you look ahead during training, right? And just randomize this, and that would probably work even better. Yeah. It's a question. Yeah.
Who controls the database if there's conflicting sources of truth?
Who controls the database? You as a user. I think it depends. The owner of the LLM owns it. Right? So one advantage actually also is for LLMs is you could ship the network and you put in your own database, right? So you as a company, you say, this is what I want the language model to know and nothing else, right? And you just populate it and throw out everything that it's not supposed to know.
In the LLM case, you're trying to reduce the size of the model, but it seems like you also have to train the model on what the keys of those entities are. Like the model knows about Napoleon, but if you say have a larger user database and you want to push as much as you can into the triplets, like how do you tell it?
Very good question. So where do the keys come from? So they're either common knowledge or they're stuff that already happened earlier in the text. So you can look things up, and then actually when you look things up, you actually get new keys to do new lookups. So you can have chains of reasoning that way. I think I'm out of time. Okay, last question, I guess.
So I really like the latent diffusion part, especially called a planner, right? It is indeed a planner to decide what to schedule, which token comes out, but it's a fixed cost, right? For no matter what you have in the prefix, your latent diffusion still run, let's say, 100 steps to denoise. Have you tried to see if you compress the diffusion model's number of steps, would you get a better quality or worse quality? Because in the end of the day, you still want to save the amount of planning flops.
Yeah, let me just say one thing. The diffusion model actually here, so you can vary how quickly, how aggressively you want to decode. So you can do it in 10 steps or 100 steps. And it's faster than you think because it attends over all, like while you're diffusing, you actually do attention over all the previous tokens. So you get a very strong hint of, there's context basically, right? Which usually speeds up diffusion models a lot. But it's a parameter you can set. I think we're done.
Okay, yeah, let's thank Killian again.